So if this is my vector A, there are a couple of different ways that I can represent that vector. I can write it as a row vector, meaning my first element is how far we came to the right, and my second element is how far we went up. The other common notation is using our standard basis, and oftentimes this is the way we would write it in physics, would be to take that first component and write that as 5i hat, and take our second component and make that 2j hat. And this is another common way that we would write out a vector. So let me take another vector and let's make B something like that. And my B vector here, I'm going to call, let's say this is 3 and that's 4. So my B vector would be the vector 3, 4 as a row vector, and that seems to be the standard notation that our textbook is using, is to write it as a row vector. Again, switching to the standard basis, or the way that we would often write it in physics, this would look like 3i plus 4j. So let's talk about some of the things that we can do with these two vectors. One thing that we might be asked to find is the magnitude or the length of these vectors. And when I'm looking for the magnitude or the length, essentially we're doing the Pythagorean theorem. So if I think about, for that vector A, if I dropped a little line down here, that's the hypotenuse of a triangle whose base is 5 and height is 2. So that length of the vector A, we denote usually with double bars and say, well, that's going to come from the Pythagorean theorem. So we'll be taking the square root of 5 squared plus 2 squared, or just looking at the two components. I could also take the magnitude of B in the same way. So I can say that my length or magnitude of the vector B is equal to the square root of 3 squared plus 4 squared. We can also talk about things in relation to each other. So I can talk about addition and subtraction of these vectors, or we can talk about linear combinations of these vectors. Let's start with addition. If I add the vectors A plus B, to do that sort of using this notation, I actually think it's easiest to use the 5i plus 2j, the ij versions of this. So to back up for a second, there's a question about a double bar or a single bar. Both are correct notation. So usually it comes down to whether we're using a notation where we're making the letters bold, or we're using a notation where we're putting a vector hat on top. But both are absolutely correct notations, and everyone's going to know what you mean by either one. And the textbook actually uses both, depending on which section you're reading. So back to, if I'm going to add these two vectors. If I'm adding these two vectors, not graphically, but just adding them based on their vector components, I'm going to treat this like I would any other addition problem. I'm going to take what I have for A, which is 5i plus 2j, and add that to what B equals, 3i plus 4j. And then if I group those together, since these are both i's, pulling those together, I'm looking at 8i plus, pulling the j's together, 6j. And that would be my addition vector for A plus B. If I did that graphically, for A plus B, I'm going to take that A vector, and then I'm going to imagine picking up my B vector and setting it over here. So I'm keeping the same angle and the same length. I'm just moving the vector from here to here. And then our new vector A plus B would go from the end of A to that tip of B. And that would be my vector A plus B. And we can look at that geometrically and kind of get back to this component piece, because we know that the vector B moves 3 to the right and up 4. So if I'm already at an x value of 3 and I move 3 more to the right, then I should be 8 over total, which is what we got. And in the vertical direction, I know that I was already at 2, and then I went 4 more up. So overall, my total vertical gain here should be that 6J. I'm going to start this by just thinking about, if I multiply A times B in the normal way that we multiply A times B, this would look like, oh, by the way, I should have mentioned this. Don't take notes on this part. There's a much faster way to get to the answer. So just watch this and then we'll talk about the faster way in a second. So if I multiplied A times B, then this would look like 5I plus 2J times 3I plus 4J. Now, if I multiply this in the normal way, I'm going to end up distributing things out. So I'd have 5I times 3I, or 15I dotted with I, plus 5I times 4J, so that's 20I dotted with J. These two together, I'm looking at 3J plus 3I, so that's 6J dotted with I, and then finally I will have 8J dotted with J. Now, I've been saying that word dot because we are doing a dot product here, and in lecture today, or if you've been reading along in the textbook, we were introduced to the dot product through the law of cosines. And our definition for U dotted with V, so those are both vectors, U dotted with V is equal to the magnitude of U, and I'll go ahead and use a single line, the magnitude of U times the magnitude of V times cosine of the angle between them. Well, if I come back over here and I think about this definition for the dot product, I dotted with I, well, that's the same vector. So if I dot a vector with itself, thinking about this notation-wise, the angle between them is 0. So if I dot a vector with itself, cosine of 0 is 1. And we're kind of ignoring this piece. So we just end up with the magnitude of the vector times the magnitude of the vector. Well, let's look at what the magnitude of the I vector is. If I take the magnitude of I hat, that would be the square root of 1 squared plus 0 squared. So that magnitude is 1. When I do I dotted with I, it turns into 1. Now let's look at J dotted with J. Almost the same thing is going to happen, but when I look at the magnitude of J, my 0 and my 1 are backwards. I'd have a 0 squared plus a 1 squared. I'd still get a magnitude of 1. So that J dotted with J over there, that's a 1. Now for these two pieces, if I have I hat dotted with J hat, given our standard basis, I points directly to the right and j points directly up. That means those two vectors are at a 90-degree angle with each other. Cosine of 90 degrees is 0. And this is kind of what we were getting at right at the end of lecture today. So if I have two vectors that are orthogonal or perpendicular, meaning there's a 90-degree angle between them, their dot product has to be 0 because this cosine of 90 degrees will go to 0. So that means this term goes to 0 and this term goes to 0, which leaves us with A dotted with B is equal to 15 plus 8. And remember that 15 came from multiplying my two I component coefficients together, and that 8 came from multiplying my two j coefficient components together. So our shortcut for doing the dot product, we don't have to follow this formula. We often don't know the angle between them, but mechanically we calculate the dot product by doing the I components multiplied together plus our j components multiplied together.